I want to mention I'm trying to get grading caught up. I was working on it this morning. I have probably half a dozen assignments that still need to be graded. And I haven't looked at any of the muscle video stuff. But otherwise I've caught up. I went through and graded the muscle anatomy and muscle physiology assignments that had been handed in, which was most of what I had left to do. I did have a meeting that I just came from that I had to kind of focus on preparing for that. So I'll continue trying to grade things. And tomorrow morning I have to proctor somebody else's exam while she's tied up doing something else during the day. So that's an hour and a half of me sitting there doing nothing, and I'll bring in one of my Chromebooks and I'll do some grading then. So I should get up to date on your stuff tomorrow, except for the videos. I can't sit there and watch videos on a laptop in front of people while they're taking a test. So, but I'll get everything else taken care of tomorrow. I would imagine last week I went through the stuff that we have coming up, talked about the cumulative final test and that stuff, right?
Yeah.
Yes? Okay. I keep forgetting to do this. So while I'm thinking about this, let me just quickly get rid of these extra credit due dates that don't apply anymore. Where'd it go? Just to kind of touch base again on where we are, we're doing excitable membranes today. Then next week we'll be looking at the nervous system in a little bit more broader terms. And then the week after that, looking at clinical correlations or neurological correlates to what's going on. The nervous tissue chapter assignments, which were in last week's folder, weren't due today. They're due before their due date is for next week, the 26th. And then the assignments that are in next week's folder on the nervous system, that's the last set of chapter assignments you have for the semester. There's not assignments in the neurological correlates folder. There was a learning pod assignment in there, but of course, we're not doing learning pods anymore, so there's no assignments in that folder there. And then the following week, we'll be doing the second lab practical during the final exam period, which that's Wednesday, right? The 13th? Yeah. Actually, let me, every so often, or not every so often, probably about half of the semesters I get the final exam date wrong for this class. Because the way the schedule works has changed a little bit. So let me just verify that. Okay, yeah, it is definitely the 13th. That will be for your class and my Wednesday afternoon class. You'll both be taking the second practical at the same time in there. I think the one issue to deal with is that there are 24 seats in here. And there's actually, what would that be? 28 students. So I'll have to stagger things. What I usually do is between two groups, Monday and Wednesday, have the Monday class come in first. So you guys will go ahead and come in at 1:35 for that. You can use the whole time if you need to, up to 3:25, although I expect most people will be done with it within about an hour. And then at 2:30, I'll have the other half of the class come in, or the other class come in. You'll be able to, like I said, take the whole time if you need it. You have the hour and 50 minutes worth of time available if you need it, but I'll probably stagger it that way. So in the second hour, more students will be coming in to take it there too. Just most of you will be done with yours by that time, and so there will be seats available for other people to come in. But that's the way that'll work. If I have to make a change, it won't change anything for you. If I find out that there will only actually be 24 students coming in, then everybody will come at 1:30. But if that happens, that doesn't affect you because you're coming at 1:30 for that anyways. And to remind you, that is the last chance you have to complete any online work on Blackboard. The lab practical online assignment and the cumulative final both have as their due date and time 1:35 on the 13th. So those have to be done by then, and that's really the due date for everything. If you didn't complete anything else on Blackboard by its due date, you can still complete it by that time. But when you're in here taking the test, I'll get on Blackboard here and I'll make the course unavailable. You won't be able to get back in there to look at anything, to work on anything, and I'll be able to finish up grading that way. So just to remind you, all work has to be done by the time you come in for the second practical in class component. Okay. This week's folder, which technically I haven't changed it to the this week pointer, but it is what we're doing now, is on the excitable membranes. There is an overview assignment. If you go into this folder now, probably you'll just see this statement that there is an overview assignment, but you won't see a link to that assignment, which is hidden until you've completed the nervous tissue part 4 assignment. The grade on that doesn't have any effect. Just completing it, you'll be able to go on. And because the grade doesn't have any effect on it, you won't have to wait for me to finish grading it for you to get in to do that excitable membranes overview assignment. You had an overview assignment earlier in the semester for after chapter 4 that was looking at the levels of organization. This is the same sort of thing. This is an overview assignment that goes looks at really the electrical signaling in both muscle and nervous tissue. So some of it goes back to the excitability part of what's covered in the muscle chapter. Not strictly the excitability, but the stuff that's related to that, meaning how it might cause contraction and that sort of thing, as well as activity. I mean, the stuff that we're talking about today for nervous systems, nervous tissue activity. So be aware that that's in there. While I'm in this folder here, let me also point out there's a lab quiz here. It says neuroanatomy lab quiz. It has questions about the lab material we did last week, which was looking at the micrographs of nervous tissue. But it also has questions going into the anatomy of the system a bit more. What I've done in the past with my more traditional lecture lab sequence course, 1 week we do the tissue stuff like we did last week, and then the next week we look at brain models and get to know more of the gross anatomy of the nervous system. With this hybrid version, today Ashley is going to spend, we're going to spend the whole time dealing with how electrical activity works in this tissue. It's a somewhat complex tissue, a somewhat complex topic, and we need the whole day to deal with it. So I believe right now the due date for that lab quiz is next week, but we'll actually be doing that material next week when we look at the nervous system. So I'll just need to push that due date back a week. So what's today? 22nd? So the 27th is next week's class. Excuse me?
Yeah, you're right.
Thank you. So right now that lab quiz says that it's due midnight on the 26th. I'll push that back so it'll be due midnight on May 2nd, I think it is. That's close, okay. So yeah, I'll push that back. I haven't done it yet. If you open up that assignment and it still says that it's due on the 26th, please let me know. That means that I forgot to change the due date, but I'll probably do it right after class or maybe during the break today, because I know that we're not going to get to that material today. So the material we are dealing with is about electrical activity. And as I was doing this last week for, I think, my night class, I came across a YouTube video that I'd actually like to start with here. Let me, nope. Oh, that was stupid. I should have gone a different way, but anybody want to watch the new Star Wars trailer? It's one of these two. Let me see what happens. Okay, I'll know it pretty quickly. I know how it starts out. So
in today's asset class, we're going to explore the difference between dreams and possibilities. You may.
Okay. And that's not it. I'm bad. No. So let me try this other one.
How does the pain you experience when...
Okay, so let me play this one for you. The way that I've set things up in the book for this material, it's starts with sort of an explanation of your basic input-output connections to the brain. The picture you might have noticed in the book has a hand under water in the shower, testing the temperature of it. And the idea there is to set up sort of what the electrical activity is for. Obviously this video starts here with this girl apparently burning her hand on the stove. But it has drawn in the nerve coming from her fingertips that's carrying the information from the heat or pain that she's experiencing, going to the spinal cord, and then a nerve going out to the biceps brachii that's going to help withdraw that hand. So this is an even simpler idea of the kind of connections that'll involve a lot of the players in the system. So it's sort of the same approach, is to start by looking at, here's some nervous system activity. What's the underlying activity that's causing that? So let me play this, and I'll use it sort of as a start for the discussion of what we're looking at here.
You burn your hand results so quickly in an action by your muscles. Many animals respond to environmental stimuli using specialized cells called neurons. A stimulus is detected by sensory receptors and the body responds through motor effectors. These cells working together allow you to respond very quickly to threats. When you touch something hot, heat receptors of a sensory neuron detect the stimuli and send the information of heat to an interneuron in your central nervous system. From there, a motor neuron sends a response from your central nervous system to the skeletal muscles in your arm, causing them to contract and pull your hand away. The fundamental process of neural transmission that underlies this action occurs in all neurons of the body. Neurons transmit this information through changes in the electrical potential of the membrane by the movement of ions across the membrane. An electrochemical gradient governs the movement of these ions, resulting in an electrical impulse. The resting membrane potential in a neuron, when the cell is not firing an impulse, is established by the unequal distribution of sodium ions outside of the cell and potassium ions inside the cell, making the outside of the cell more positively charged compared to the inside. The electrochemical gradient is established and maintained by an enzyme called sodium-potassium ATPase. When a neuron is stimulated, sodium ion channels open and sodium ions flow into the cell. This leads to a change in the electrical potential across the membrane called depolarization. The depolarizing electrical potential travels down the dendrites and over the cell body. Multiple electrical potentials will combine at the axon hillock in a process called summation. If the depolarization is large enough, an action potential is triggered. Action potentials are all or none electrical impulses that maintain their amplitude and strength down the length of the axon. The action potential travels down the axon when the depolarization of an area of membrane causes adjacent voltage-gated sodium ion channels to open. The influx of sodium ions results in membrane depolarization along the membrane. After a short delay, potassium ion channels open and potassium ions flow out, repolarizing the membrane. For the neuron to fire again, the resting membrane potential needs to be reestablished. Sodium-potassium ATPase is used to move sodium and potassium ions against their concentration gradients, reestablishing the resting membrane potential. As the action potential moves down the axon, ions are diffusing only a short distance, allowing the signal to move quickly. At the axon terminal, the electrical impulse passes to another cell at a cellular connection called a synapse. The space between the presynaptic neuron and a postsynaptic cell is called the synaptic cleft. The presynaptic neuron contains signal molecules called neurotransmitters that are packaged inside vesicles. When an action potential reaches the end of a neuron, neurotransmitters are released by exocytosis from the neuron into the synaptic cleft. Neurotransmitters bind to the adjacent cell at receptor sites attached to ion channels. The channels open, allowing the movement of ions into or out of the effector cell, which alters its membrane potential, thereby transmitting the signal from the neuron to the effector cell. Because nerve impulses move very rapidly down the axon of a neuron and move from cell to cell across synapses, you react quickly to a stimulus, like burning your finger.
Okay, so what was that? 4.25 minutes. This actually kind of goes through all of the information that I want to talk about. So
Potential of the membrane by the
so actually, I kind of want to use the video as a framework to explain what's going on. I kind of approached this material each semester a little bit differently. And I've never quite happened across what I think is a great way to do this. And so with this video, which this is the first year I've known this video to be available. on YouTube. And I think it's a really good, quick run through of all the information. And I want to spend a little bit of time talking about what's going on here, providing a bit more explanation about things. And I think it'll do pretty well to set up the information we need to cover today. And that might even mean that we get to do things a little quicker. Now, what were we going to talk about? Like I said, the way that this sets up things is very similar to what the book has, what I put in the book when I wrote these chapters, in sort of setting up the idea. Let me go back to this picture here, of what's involved, the circuit, so to speak, here. So there's information coming from the outside into the central nervous system, which causes a response to that information. So pulling a hand away from the hot stove, for instance. The different sources that deal with this information will sort of present that in different ways, and the one that's in the textbook was sort of the approach I chose to use. I didn't really want to use a simple reflex like that, because also I want to talk about some of the more complex arrangements and connections in the system. And depending on where we actually are today, I might spend a little bit of time talking about that, or I might leave it for next week, because really it's mostly to set up the material for next week. So where this starts is to just talk about the basis of the electrical activity. And what's happening is the electrical activity is based on what's going on at the membrane. So we have the extracellular and the intracellular space noted here. And on the inner side of the membrane, there's a negative charge, and on the outer side, there's a positive charge. Now, really what we're talking about here is a distribution of charge. And some of what I'm going to be doing here today is to just define some terms that help us understand what's going on here. So the basis of this, what's going on at the membrane, is found in the term membrane potential, which is a distribution of charge across the membrane. Conventionally, it is a comparison of the inside versus outside. What that means is the distribution of charge is defined as a voltage, and the voltage amount is the difference between the inside and the outside. If the outside is considered zero, then the voltage is how much different the inside is. Okay. So that's what I mean by inside versus outside. In a picture like this, where they have negative charges drawn on the inside of the membrane and positive on the outside, that actually doesn't mean that there's an absolute voltage on one side versus or the other of the membrane. It's really just compared to outside, the inside is negative. And so if you're going to put negative signs inside, then you would put positive signs outside. More accurately, what we're talking about is the outside's neutral, or has no charge, and the inside is a negative charge relative to that. One way of describing what's going on here is to use some metaphors that come right out of the physics of electricity. The physics of electricity. And what we're describing here with the membrane is really just a battery. Okay? In a battery, you have a positive and a negative pole, okay? Just like there's a positive and negative side of the membrane. Again, really the positive and negative here that we're seeing is a convenience for describing it. It's the inside is negative relative to the outside. But the membrane potential, it's potential energy, if you will, stored across the membrane, just like energy stored in a battery. And we measure this in a unit based on voltage. Does anybody know what voltage we have in this battery right here? What is stored in this battery? It's a AA battery.
Oh, yeah.
How much?
What's the voltage in a battery?
It's more.
Yeah, so I figured you'd probably know. Most of the time when I ask that question, nobody knows. But it says it on every battery, and I've always known it because I've looked at batteries. And right here it says AA. It has a couple of codes describing what type of battery it is, and it says 1.5 volts. So I do that, and nobody says, and I knew you'd recognize it because you're an observant kind of guy. But when I hold this up and people know, nobody knows what the voltage is, I then go to, okay, what's the voltage here? And everybody knows this one, right? Yeah, it's a 9-volt battery. It's in the name. This just has positive and negative poles on the same side of the battery rather than opposite sides of the battery, but it's the same idea. Now, in truth, this battery probably has no charge left to it. It's been on my cart for years. I think it's one that I got from one of the clickers that we use when the clicker died and I had to replace the batteries. I think that's one of the batteries from there. So I'm sure it has actually no charge left in it, but still the metaphor works here. The charge distributed across the membrane, what we call the membrane potential, is essentially like a battery. Okay. Now, one thing I really like about this video is this thing right here. The whole time that it's showing the membrane and pointing out what's happening, this part of the membrane is always in motion. This is the sodium-potassium ATPase, or sometimes it's just called the sodium-potassium pump. It's been stylized and schematized a little bit for the sake of making this picture, but what they demonstrate here is essentially what the thing does. It's a protein that's in the membrane, and there's 3 spots for sodium ions to bind to and 2 spots for potassium ions to bind to. When it hydrolyzes ATP, it's able to pump the sodium out of the cell and the potassium into the cell. Now, I think I just said it's also called the sodium-potassium pump. Pumps are molecules that use energy to push ions against their concentration gradient. Okay. So this is pumping sodium out of the cell, which means it has to expend energy doing that because there's more sodium outside the cell than inside the cell. In fact, there's about 10 times more sodium outside the cell than inside the cell. That's a pretty strong concentration gradient. Okay. If there's ever a channel that opens up that allows sodium across, then sodium is going to rush into the cell very quickly. Okay. And it's pumping 2 potassiums into the cell. The concentration gradient for potassium isn't quite as strong as for sodium. It's not 10 times different in concentration. It might be more like 4 or 5 or 7. I can't remember the exact number, but it's less than 10. But still, it's pretty strong in that there's more potassium inside than outside the cell. And when potassium ion channels open, then the potassium will rush out of the cell. Okay. And that's really the basis of the electrical signaling. Okay. And it's all based on this idea of the membrane potential. Okay. And it's measured in millivolts. So the batteries I was just talking about, 1.5 or 9 volts. The amount of charge that we see distributed across the membrane here is really pretty small. A millivolt is 1/1000th of a volt. Okay. Now, what that value is at any given time depends on exactly what we're talking about happening here. So let me start with what's called the resting membrane potential. And this is the distribution of charge which is measured in millivolts. Let me just, yeah, millivolts. Across the membrane, and the cell is at rest. Nothing's happening. I shouldn't say nothing's happening, but the cell is not creating an electrical signal. It's just sitting there doing nothing. Again, the convention is comparing the inside versus the outside. And so the usual charge, or the one we'll always deal with, is negative 70 millivolts. Now, there are situations where there are cells that have a resting membrane potential that's not negative 70 millivolts, but that's the convention we're going to use. And it's a pretty standard convention. Most sources that are talking about this basic information are going to talk about negative 70 millivolts as being the resting membrane potential. So it's a nice safe place to stay. But there are exceptions to that. If you see something talking about resting membrane potential and it provides a different number, don't freak out. It's just that there is some variation in the types of cells that can be electrically active like this. Okay. Now, what the video here is showing happening, and let me see if I can get to a spot where it's happening, where sodium's entering into the cell, or oh, I thought I had it right there. Okay. So sodium's entering into the cell, or potassium is leaving the cell. Those events are part of what we call the action potential. And this is a series of changes in voltage that results in a nerve impulse, or an electrical signal. When we say action potential, it's almost an interchangeable term with nerve impulse or electrical signal. It's just the more formal name for what's going on here. In the video there, it mentions that it's an all or none event, which means if it starts, it's going to run to completion. Okay, it might not ever start, but once it does, it goes all the way. In the video up in the corner, when they're talking about the sodium and potassium going through their respective channels, there's this graph that's represented up here. Okay, and I'm going to just pull up from the textbook the same graph, just represented in the textbook here. So this graph here is essentially the graph that's in the top corner of the video that we just looked at. Okay. But it's labeled a little bit more. Okay. So we have negative 70 marked on the x-axis, and there's a flat line going from that, showing that nothing's happening in the cell. That's the resting potential. Okay. And until something happens, that's what we're going to measure electrically from any cell. There has to be some change that's going to result in the action potential. Now, I'll get into explaining how this happens a little bit later, but as soon as the line leaves the negative 70 value and it goes up to where this dotted line is at negative 55, that's the change that's causing it to happen. We'll actually go back and talk about that a little bit later on. what we really want to think about is what's happening from the negative 55 on until we get back to the negative 70 resting potential. So everything that we see here where the membrane potential goes up and then comes back down and dips down kind of low and then hits 70 again. That curve, that graph, or the events that are in that graph, that's the action potential. Okay. I haven't gotten to describing it yet, but it's initiated by some event or stimulus. Okay, and I'll talk about that a little bit later on. It starts with sodium ions entering the cell, making it more positive inside. Okay. So here we have sodium channels open and sodium ions are entering into the cell. Remember, they have a 10-fold concentration gradient. So there's a very strong impulse or impetus, force, whatever you want to call it, pushing them into the cell. And when that happens, we go from that threshold level, negative 55, up to the peak of the action potential of positive 30. And that's what we call depolarization. Okay. Now, the membrane is at a fairly negative charge. So it's polarized. It's away from zero. Depolarization makes it become more positive in moving towards zero. It goes past that to positive 30, but we still call that depolarization. Okay, so that's the first part of the action potential when everything goes up. Okay. Whoops. So depolarization is when the membrane goes from negative 55 millivolts to positive 30 millivolts. And then potassium ions leave the cell, making it negative again. So depolarization is when we go up to the peak. And then when things turn around and we go from positive 30 back down, that's what we call repolarization. And that's the result of potassium leaving the cell. Okay, what we see in the video right here. Okay. Which, here we go. Had to go jump to another frame. So up in the graph in the corner, we now see a highlighted region from the peak of the action potential as it's going all the way down. That's what we call repolarization. Repolarization is when the membrane goes from positive 30 millivolts to a very negative value. Now, I'm not putting a specific number here. I just say very negative value because in different situations, it might be different values, but it's less than negative 70. So this very negative value is more negative than negative 70 millivolts. It's below resting potential. And is called hyperpolarization. Okay. So here's positive 30 where the peak was. At the end of depolarization, things turn around and the potassium leaves the cell, making it more negative again. It actually goes a little too far and makes it overly negative. It goes past resting potential. And like I said, we don't really care what this value is. Some sources will probably call it negative 80. Some might call it negative 90, whatever. very negative. And then it returns, sort of slowly gets back to the resting potential of -70. Okay, that's when hyperpolarization is over. That's when the action potential is over. Okay. So the action potential is finished when the membrane is back to rest. It's back to -70. So we can look at a graph like this and see the change in voltage. That is one way of defining the action potential. We can look at, a video. Oh, shoot, I closed the video. What happened to the video? Okay. Oh, I know what I did, but. Oh, there it is, yeah. That's not the video. Where'd the video go? Darn it. Sorry, I closed the video by accident. There we go.
Here in my garage, just bought this new lamp.
Should have saw on Ghost Street.
Sorry?
You should saw Ghost Street and box on the ads. You should. It's on Ghost Street.
Oh, I don't do that. Can't do that on a school computer. I can't install other stuff on it, so it violates the IT thing. It'd be great if we get rid of the ads, but we can't. Anyway, so where were we? Okay, repolarization when potassium is leaving and things go back down. I don't think in this video, yeah, well, actually, yeah. So in this video, they jump from the repolarization part of the curve right over to when it's back to resting potential. They don't mention in this video the hyperpolarization, but it's in the graph just the same, even though they skip over it, which is fine because they're trying to say as much as they can in 4 minutes, and the hyperpolarization isn't critical to what's going on. What's really critical is the idea that things are getting very positive and then very negative very rapidly. Okay, and then we get back to rest. Let's see. So this just shows this last thing, kind of to round out a little understanding of this. We see, say, the axon of a neuron here with the green sodium and the purple potassium ion channels in there. And we see, that's why. It runs pretty quickly, so I skipped over it. So they show that the sodium moves quickly through from one side of the membrane to the other, and the potassium moves quickly from one side to the other. And it says down here, you can see in the subtitles, ions are diffusing only a short distance, allowing the signal to move quickly. This is just what's happening right at the membrane. The membrane itself is not very thick. So there's sodium on one side and potassium on the other side, and it quickly moves through the channels to the other side, making this all happen kind of instantaneously. What in the world did I get here? Weird. Going back through closed tabs, and I started getting really weird ones. Let me get back to where we were. So we're looking at this action potential thing. On the x-axis of this graph, and on the graph in the video also, it just says time is passing. And actually in the video one, it says in milliseconds. The time that this takes to occur is like a couple of milliseconds long. Okay. So this is a very, very rapid signal. And we just sort of lengthen the time part of this graph so we can see the events separated out. But it would all happen way too quickly for you to see any particular event. In fact, when somebody's studying this in a real system, they can see this on a graph on an oscilloscope, but it happens so fast that you can't really see the events. The electrical signal, the recording electrodes that are measuring the electrical signal is hooked up to a speaker. So when an action potential fires off, a researcher studying this will actually hear a little pop on a speaker. And it's an easier way for us to actually see what's happening. Otherwise, the data has to be collected and analyzed by a computer. Okay. But this is happening very quickly, is the point I'm making here. So I was talking about what's happening at the membrane and the action potential. I actually kind of skipped over a little bit at the very beginning of this video. Maybe not at the very beginning. So it starts off by just mentioning the ions, and I think it backs out to look at the cell. There we go. So here it's looking at the cell. It's just defined, the membrane potential and depolarization. And then what it shows is little bright spots, which is representing some change in voltage of the membrane. And they're pointing out that it's happening in various places in the cell body and the dendrites. And then those bright spots start to move along the cell until they get to where the axon comes off the cell. Okay. And it's saying that if the depolarization is large enough, then the action potential is triggered. And that gets to the part at the beginning that I said we'd talk about a little bit later. Okay, so some event or stimulus has to occur to get us from resting to threshold, the dotted line there at -55. And what happened? Oh no, my greatest fear. I apparently erased all of the stuff that I wrote.
Why don't you do it in Word?
I have my reasons. So I was talking about the membrane potential and the action potential, which are saved in the video, which we can't access right now because it's still recording, but we'll get to that later on. Probably over the break, I'll go ahead and write back in what I had earlier if you didn't get it all. The next thing I want to talk about is what's called a graded potential. And this is, again, a change in membrane voltage that varies in size based on the stimulus. What they're showing here, all these bright spots on the membrane that are moving towards this spot on the axon, or at the beginning of the axon, those are graded potentials. They can be weak, which in this picture is kind of represented by a paler shining color, or they can be stronger as the dot gets brighter like this. But we can see the bright spots moving in. They fade a little bit as they get towards this spot, but as they all come together there, they're added together, which is called summation. Okay, and graded potentials, let me pull this image up, can be of different sizes. So they can be mild or small, medium or large, kind of the way that they're shown here. And they can be in varying lengths of time. So here's a small one that says, let's say, is only getting from -70 to -64. Here's one that's getting from -70 to -60. Here's one that's getting from -70 all the way up to negative, call it 51 there. So they can be differing heights based on the strength of the stimulus that's causing them. And they can also be differing times. So this one is actually was supposed to be the same size as this height, but it's wider, just that the event or the stimulus is lasting longer, is what that's suggesting. So this really tall one, the last one of the depolarizing graded potentials, passes threshold, which means that it would cause an action potential to occur. The other ones aren't strong enough to do that, but if we added them up, they'd be that strong. So for instance, the first two, the first one, let's say that's getting from -70 to -64, so it's a 6 millivolt depolarization. And the next one's getting from -70 to -60, so it's a 10 millivolt depolarization. If we add 10 and 6 together, then we get 16, and we'd hit, well, we go past the -55 threshold. So we can summate those together and get to threshold. And that's what's suggested in the picture here. The individual things here, as they're fading into lighter and lighter colors, can summate and end up really depolarizing this until the action potential, should happen any second now, travels down the axon there. Okay. So everything that's leading up to that point, all of these little bright spots that are moving towards this point here, those are graded potentials. And they can be of differing strength depending on what's causing them. Okay. So if we go back to the little girl touching the hot stove, or the picture in the book of testing the heat of the water in a shower, the stronger the stimulus, the stronger the graded potential is going to be, and the more likely an action potential is going to occur. So with the girl that's touching the hot stove in this video, it's probably a really strong stimulus, and it causes a graded potential that starts an action potential that travels down. Let me go to. So it starts an action potential that travels along the length of the axon, gets here, and eventually starts another action potential that travels back to the muscle along another nerve and causes contraction. So if the stimulus is strong enough, it'll send a signal down there. If she'd been reaching out to touch this stovetop and or pan, let's say, and the stove's turned off, or it's cooled down at least, then she's not going to have the same reflexive withdrawal. It's not going to be a strong enough stimulus to elicit the response. Now, what I'm saying here is actually not perfectly what I'm talking about, but trying to get it to a real world example. Let's just say that until it's a burning hot stimulus, there's not going to be enough of a graded potential, enough of a signal to make the action potential travel along the length of the axon to its target here, and then send that signal on and send that signal on to the next one. Okay. Actually, what's happening is she can feel the temperature of whatever that is, whether it's hot or cold or lukewarm. It's just the connections in the system aren't going to make her withdraw unless it's a really strong signal. Okay? So somewhere along the way, the stimulus has to be long enough to elicit the response. If she's just going up there and reaching and touching something that's actually not hot, she's not going to have the reflex that's described here. Okay. Now, as we're looking at these graded potentials, the first four are grouped as depolarizing graded potentials, meaning that they make the membrane less negative. It goes from -70 to -64, or to -60, or to -61, or to -51, or whatever it might be. That's what depolarization is, making it less negative. It's also possible for graded potentials to go in the other direction, to hyperpolarize. Now, really the point of graded potentials is to reach threshold, or to influence the cell generating an action potential. And so depolarizing graded potentials are going to hopefully trigger that action potential, maybe by themselves or maybe by adding up together. Hyperpolarizing graded potentials are going to have the opposite effect. They're going to make it less likely for the membrane to hit threshold and therefore see any kind of response or action potential. So graded potentials can be depolarizing, which means the membrane becomes less negative, or they can be hyperpolarizing, which means the membrane becomes more negative. Okay. Adding these together, which is summation, will determine if the cell reaches threshold, -55 millivolts, and an action potential is started. So it's been erased off the screen from when I wrote it earlier, but action potentials are all or none events. Okay, so if the graded potentials summed together don't reach -55 millivolts at the membrane, then the action potential doesn't start. But once the graded potentials add up to -55 millivolt membrane potential, then the action potential starts, and it does exactly what I just ran through. Sodium rushes into the cell, and it goes all the way to +30, and then potassium leaves the cell and comes back down to negative, more negative in resting potential, and eventually it corrects itself there. Okay. So, in talking about these three things, and I'll have to add the stuff back in here about membrane and action potentials, this is essentially what's happening to generate the signals. Okay, the membrane is sitting at rest, and come to think of it, there should be a resting potential in here too. So it's sitting at rest, and then the graded potentials will cause the membrane to change its voltage. If that's in a positive direction and get to -55 millivolts, then the action potential occurs. Okay, that's essentially what's happening here. That's essentially what this video has been showing us here. Okay. At the end of the video, actually, not the absolute end, but towards the end, somewhere in here, it starts to talk about here, the synapse. So here's an action potential, a bright spot that's traveled along this axon, and it's gotten to where the axon connects to another cell. And so here's another axon terminal, which we see, it's making a synapse with this particular cell. And as we zoom in and look at this, we see vesicles containing a chemical, which is neurotransmitters, which will be released across the synaptic cleft to interact with the membrane on the other side of the synapse. And so here we see the vesicles containing the neurotransmitter getting to the membrane. Let me play that out. So they release their contents through exocytosis, and the neurotransmitter gets into the synaptic cleft, where it then diffuses over to its receptor. Okay, so we see one of those molecules right here that's bound to the receptor, and the other two are doing that. And that opens the channel. Okay. Now, we actually looked at this before. Back in the musculature, we talked about the neuromuscular junction, and that's essentially what this is. In this picture and in this video, they're showing one neuron communicating with another neuron, but it just as easily we could be looking at a neuron that's communicating with a muscle cell. And that's what's going on with the neuromuscular junction we already talked about. In this video, they're showing one molecule of neurotransmitter binding to the receptor, but really at the neuromuscular junction that we talked about, there's two molecules that bind there. That's probably what they should have illustrated here. It's a more common example, but whatever it is, the chemical binds to the receptor, and it is an ion channel that opens up and allows sodium into this cell. And that sodium, when it gets into this cell, is going to depolarize the target cell. And if that depolarization is enough to reach threshold, then we'll start another action potential.
Why is the sodium depicted as being larger than the
They're trying to make it big enough to write Na on the thing. But yes, definitely a sodium ion is going to be minuscule compared to a neurotransmitter molecule, or for that matter, the ion channel there. But yeah, for the sake of labeling it, they made it big enough to write on it. So I kind of skipped over that. And so the sodium's gotten into the cell, so the cell's going to be depolarized. And then we see, after they pulled out a little bit later, an action potential moving along. Okay. So that's sort of going into a little bit more depth what this video is talking about. There's more to explain how this is working, which I'll get to in a little bit. But I started off by just playing the video, and then I wanted to talk a little bit more about what's happening in the video. Are there any questions about what I've seen here? Do you understand what's going on? Now, earlier when I was talking about the membrane and potentials and that sort of thing, I pulled out the battery to talk about that as a metaphor. When I first learned about this stuff, or probably when I second learned about this stuff, to tell you the truth, I don't remember learning this in college. I remember when we went into it in graduate school in a lot more depth. And so that kind of overshadows any learning I had before that. And in graduate school, when we're learning it in the very physical, electric circuit kind of way. It's a really in-depth way to understand it. But my teachers, when they were explaining it that way, weren't willing to admit that they were really talking about a metaphor. Okay? Like I just said, that the membrane is like a battery. The membrane potential is charge that's stored up across the membrane, just like charge is stored up in the battery. And so it's often described using these electrical metaphors as if that's really what's happening. And to some degree, it's a little fair. It is fair to say that the movement of ions across the membrane would be just like electrons moving through a wire. And so we can describe that as a circuit, which can be open and closed when the channel's open and closed. But I think it goes a little bit too far into doing it. Probably when I first learned this in college, and like I said, I don't remember that anymore because it was overshadowed by my graduate school experience. It was probably explained much like this explained it. And it's really, I think, more straightforward to talk about this in terms of you have the membrane and there's some channels in it, and ions move in and out of the cell. Okay. There's more sodium outside than inside, and there's more potassium inside than outside. Sodium rushes in, making the cell more positive, and then potassium rushes out, making the cell, returning the cell back to its negative state. Okay. What's not really explained in this video, back here when they're talking about the membrane potential and the sodium and potassium being pumped across, sodium and potassium are both positive ions, and so sometimes students can get kind of concerned because where's the negative charge coming from? Okay. And the negative charge actually is mostly coming from negative ions that are trapped inside the cell, like proteins. Proteins tend to have a little bit of a negative charge to them, and they're much too big to leave the cell. So the inside of the cell is negative. There's also phosphate ions that are not likely to leave the cell either. And so that'll give the inside of the cell a bit of negative charge. So when sodium comes in, it offsets that negative charge, making it positive again. And then when potassium leaves, its positive charge leaving gets the cell back to its negative state, which is really because of the proteins and other things that are inside the cell that can't come out. Okay. Now, in this video where they're showing us the green sodium ion and the purple potassium ion, they've drawn these in just a kind of cartoonish way. This doesn't really represent what the ion channels look like. So I want to go to the book where it's talking about ion channels a little bit more. Okay. And like I said, I kind of changed my mind about how to present this stuff a little bit. And so the way that the book presents this is kind of different from what I've been talking about here. But so it talks about the membrane and defines membrane potential, that kind of thing. And then it talks about channels and what allows ions to cross over. This first one is called a ligand-gated channel. And when a ligand or a chemical that binds to the channel actually does bind, it causes the channel to open up so that there's a pore that ions can move in or out of the cell. Okay. This happens to be what we see at the neuromuscular junction. The ligand that's binding to it is the neurotransmitter acetylcholine. Two of them bind to this receptor, it opens up, and sodium ions can rush into the cell. Actually, what happens is positive ions move across the membrane down their concentration gradients. Sodium and calcium are more concentrated outside than inside the cell, so they enter the cell. Potassium is more concentrated inside the cell than outside, so it leaves the cell. But the most important part of that is the sodium entering the cell, which depolarizes it, and that's the start of a graded potential. Okay. Another example of a gated channel is the mechanically gated channel. This is a channel that physically changes. Mechanical forces acting on the cell will cause it to change. Now the picture here, very cartoon-like, reminds me of a trash can that has a flip-top lid. Okay, so if something happens to the cell, like when you squeeze, when you put pressure on the skin, that's going to physically deform the cell, which will potentially squeeze the channel, and the lid pops open, and now ions can move across the membrane. Okay. And again, the most important thing is the sodium entering the cell, which is going to cause depolarization. Another type, which is important to understand because it's really the basis of a lot of what goes on in the action potential, is called a voltage-gated channel. And when I first saw the artwork to this, I thought it was kind of strange, but now I feel more comfortable with it. So we have here in sort of cartoon format, the channel. It has a sort of ball and chain looking thing that's attached on the intracellular side, and the ball part is blocking the opening of the channel. Now what's holding the ball in place, this is the thing that I didn't quite get the first time I saw the artwork, are these two things sticking off on either side. And you can see that they stick through the wall of the protein, and we can see a little bit of them inside, and that's what the ball's actually attached to. When the voltage changes, so down at the bottom, you probably can't read it, but it says -70 millivolts in the first picture and -50 millivolts in the second picture. So when the voltage changes, then the shape of the channel changes. The amino acids that make up the protein have potentially positive or negative charges associated with them. And so as the membrane gets less negative, that might attract part of the protein over here, so it slides into this second position. When that happens, it releases the ball that's blocking the ion channel, and the ions can move across. Okay, so they've just sort of put in here a little bit more representation of the actual protein mechanism. It's where the protein interacts with the membrane that's changing its voltage that changes, and then the gate opens up and ions can move across. Now in this picture, they just say concentration gradient, and they have an arrow pointing out, suggesting that there's more inside than outside, and so the ions move out. They're not naming what ions these are actually here, but based on the color scheme that has been used elsewhere, and the fact that it's what it actually is, these are potassium ions. So this would be called the potassium, voltage-gated potassium channel. And so when the membrane changes from -70 to -50, it opens up and the ions go through. Okay. There's also a voltage-gated sodium channel. And there's not a picture of that here, which I kind of regret, but it's not there because it was really hard to represent in a unique kind of picture. The voltage-gated sodium channel is unique because it actually has two gates. So here we see one gate that's blocking the ion channel at one voltage, and then it's not blocking it at another voltage. With the voltage-gated sodium channel, it has two gates. So this is a cartoon. It's not necessarily exactly what the protein looks like. So this ball and chain thing might not be very accurate. But let's pretend there's a ball and chain on this side blocking the ion channel over here, and we could put another ball and chain that could block the other side too. At -70, let's say, there's a block on this side of the channel, but not on this side. The ball and chain is open, and this side of the ion channel is open. But that doesn't matter because ions can't get through the channel anyways. If the voltage changes to -55, then we'd see the same kind of change, and the gate on the inside opens up, and then ions can move across. The gate on the outside was open to begin with. The gate on the inside opens up, and ions can move across. Then we need another picture showing us when when the membrane voltage gets to +30, and that's when the ball and chain on the other side of the channel would move in and block that. Okay. So there's two gates, and so it's sensitive to two different voltages. And that's the sodium channel. Now, what's important about the voltages I just used in that example? Are you paying attention to the numbers I actually said? So this one has 50, but I actually was saying a different voltage when I was talking about the sodium one.
They're slightly different.
Right, but the numbers I used, why were those important numbers to talk about?
Those are like Westing.
So I said -70 like we see here, which is resting potential. And then when the inner side opens, I said that would be at -55. Why is -55 important? What was -55 that we saw before? Yeah, it's threshold. So At threshold, what happens is the voltage-gated sodium channel opens up. Okay. And then I said we need another picture over here, which would show what would happen at positive 30 millivolts. What's happening with the action potential at positive 30? Not just depolarization, it's the end of depolarization. So depolarization is what happens between negative 55 and positive 30. Okay. So what's happening here, what's causing the action potential to start, is we've depolarized the membrane with greater potentials until we hit threshold. And threshold is when the voltage-gated sodium channel opens. Okay. And then at positive 30, the second gate closes so that sodium stops coming into the cell. And when sodium stops coming into the cell, it's not going to keep getting more and more positive in the cell. Okay, so that ends depolarization. Repolarization is actually when potassium's leaving the cell. Okay. And I just told you that this picture, oops, in the book here, this is actually the voltage-gated potassium channel. And at negative 70, it's closed. At negative 50, that's the voltage that tells it to open. Okay. Now, it's really hard to depict in a picture, but actually it doesn't open immediately at negative 50. Okay. That's when it's told to open, but it takes about a half a millisecond for this to actually occur, okay, for all this to move. The sodium channel opens and closes instantaneously, but the potassium channel takes about a half a millisecond to open. So if we go back over here, from negative 55, we start to rapidly depolarize. We hit negative 50 pretty quick, okay, say right about there. But it takes about a half a millisecond for that channel to actually open. Okay, so a half a millisecond, time-wise, would get us to right here. Okay, that happens to be when we've hit positive 30. Okay, the timing of how slow it takes the potassium channel to open means that it opens right when we need repolarization to start. Okay. If it started sooner, then we would have potassium leaving as sodium's coming in, and while they're two different ions, they're both the same charge. So a positive charge coming in and a positive charge going out basically cancels each other out. So we don't want it to happen too soon and cancel out depolarization. You need to wait till depolarization finishes. And that happens because that channel actually takes about a half a millisecond to open. And then repolarization starts. And it brings us back down to negative 50. Now, negative 50 is the gate voltage. It opens at negative 50. If it's open and it goes past negative 50 again, it closes. It's just that it takes about a half millisecond to close, just like it took about a half a millisecond to open. So even though we hit the gate voltage right here, it doesn't really close until we get to about here, which is what allows for hyperpolarization. Okay. The potassium will keep leaving the cell even though the channels are closing. It slows down here partly because some of the channels are closing, but they're not going to be all completely closed until we get to this point, when we hit the lowest point in hyperpolarization. And then slowly the sodium is being pumped out and the potassium is being pumped in by the sodium-potassium ATPase until we get back to resting potential. Okay. So the ion channels actually play a role in, no, I should say that differently. The ion channel is the reason for the events we see in the action potential. Depolarization is between threshold and the peak of the action potential. Sodium rushes in and then it stops rushing in. And then repolarization is potassium rushing out. It starts a half millisecond after it hits its negative 50 gate voltage, and it closes half a millisecond after it hits the negative 50 gate voltage again. The first thing allows it to happen right when depolarization is over, and the second thing actually causes hyperpolarization to occur. So it sets up these events here. Now, this picture in the book and that I've been working with here. I repeat, after talking about these things, here's the same picture, but now it has some labels with it, which are explained in the figure caption down here. So we have at rest, the stimulus is applied, which causes the gradient potentials, which gets us up to threshold, and then voltage rises very quickly as sodium's rushing in, and then voltage falls as potassium's rushing out. We get to the end of the action potential as all the potassium channels have finally closed, and then it returns back to its resting level. Okay, so this is just explaining the steps in a little bit more detail. It's down here in the figure caption there. Okay. So again, let me stop to see if there's any explanation needed and any questions you have about what I've talked about here. Everybody's comfortable with this stuff? Okay. So we got a little bit late start because I was hoping more people would show up, which some people did. So I went a little bit past when I would normally take a break, only 5 or 10 minutes. So let's go ahead and take a break now, which is a good stopping point. And we'll come back and I'll finish talking about the action potential and then go on to the other things that have to go, that are going on here. So be back in here about 20 after and we'll continue on.